It's a reactant that limits what we can make for product. If you are in your car, what's the limiting reactant and what's happening in your car? Gas. Yep, there's lots of oxygen in the air. We're not going to run out of that anytime soon. The gasoline, though, could run out, and then you would be out of that reactant, and you'd no longer be running your car. If you're making a recipe, and we're just going to use French toast here because this is a recipe that I use to make French toast, and it's yummy, in addition to some cinnamon that is not on this recipe. But if you're making any type of recipe, you're going to run out of one of your reactants first if you're trying to make as much as you can of it. You're going to run out of something. And if we look at this first one, what we're going to do is do 1, 2, and 3 on the front and look at French toast. And then we'll look at 1, 2, and 3 on the back, which are very similar questions, but referring to a chemical equation. But how you think about it is the same. So some of you may have already looked at this number 1 and said, well, I think I know the answer. How many people looked at it? Who wants to tell me what they think? Milk or eggs? Okay. Anyone who said milk? You want to say milk is right. How did you figure it out? And there's more than 9 eggs? Okay. So you're saying if you take 2 1/4 cups of milk, you can you're getting 2 1/4 batches, right? So 2 1/4 batches of these French toasts will make you use 9 eggs, and you have 10. So you have extra eggs. We're assuming here that we have endless bread. We have plenty of bread, and that is not an issue. So another way to think about it, and you're not going to be able to just think it through like Kenzie did with this. Another way to think about is to do chemical reactions is stoichiometry, obviously, because stoichiometry is awesome. The great thing about limiting reactants is you get to do 2 stoichiometry problems every time. You will always take both reactants and figure out how much product it could make you. In this case, the product is French toast. Now I'll take the other reactant, how much I have, 10 eggs, and figure out how much French toast I could make with that. My ratio of milk to French toast is 1 cup per 16 pieces. My ratio of eggs is 4 eggs per 16 pieces. So these are just conversion factors, just like we use with chemical equations. If I calculate how many pieces of French toast would I get with the milk? 2 1/4 times 30 times 16? 36 is what if you type it in. What about 10 times 4 essentially? Get 40 there, right? All right. So how does this prove what Kenzie said? Well, the one that gives me the least amount of product, see, my least amount of product is 36 pieces of French toast, is the milk. So my limiting reactant is the milk. Don't circle the answer, 36 pieces of French toast. That's the next question. The question is, what's my limiting reactant? So it's got to be the eggs, the bread, or the milk. The only thing that's given to me are the milk and the eggs. So in this case, the milk is what limits me because it gives me the least amount of product. Once I make 36 pieces of French toast, I'm out. I have no more milk. Doesn't matter how many eggs or bread I have at that point. I'm done. I can't make 40. So that 40 number is just a number that you could make if you had 10 eggs, and you weren't taking into account the other reactants. So number 2, how much French toast would be expected to be made? 36 or 40? 36. The smallest amount. And that will always be the case. Because once you make that smallest amount, you're out of that reactant because that reactant is limiting you. You can no longer make any more product because that reactant is now gone. We're going to do number 3 also before we jump to the back. because we're using these same numbers. Number 3 is about percent yield, which you read about. Percent yield is equal to actual yield, which is a yield that you get for actually doing the lab. Like yesterday in your baking soda lab, you all got an actual yield. We didn't call it that. We just called it the mass that you got. When you did, after you heated the baking soda, what was the mass that your final product? That was your actual yield. To get percent yield, we take the actual yield and divide it by theoretical yield. Anyone tell me where I get that number from? The equation, or from stoichiometry. Yep. I use stoichiometry to get the theoretical yield. And all of you did that in your lab yesterday. We just didn't call it that. You did 3 equations to figure out which product was actually made and theoretically how much you should make. And most of you came very, very close to your actual yield in doing that. In this case, what is our actual yield? What am I saying? How many pieces of French toast were actually made? 33. You might say, well, why didn't we make the 36 if that's the ratio? That's ridiculous. Well, in case of French toast, maybe maybe you drop one on the floor. Maybe you just put too much batter on one of them. Maybe you just felt like you had to eat one of them before you threw it on the griddle. Something happened along the way. In chemistry, it's more about the fact that you have millions and millions and millions of molecules and atoms that have to hit each other to make a reaction go. And those millions and millions and millions of molecules, not every single one of them, of those combinations of those reactions is going to occur. So the percent yield is pretty much never 100%. The attempt is to always get close to that, because if you're trying to make aspirin or Lipitor, or you're trying to make a prescription drug, or anything that you're trying to make from raw materials, you don't want to have anything wasted. You want to make as much product as you can. That's where you're going to sell that product and make money. There's people whose job it is to increase yield, to try to figure out where they're losing any of that product. Anyway, our theoretical came from the math we just did above, 36. If I take it times 100%, I'm going to round it to 92. The reason why I say I'm rounding it to 92 is because officially with sig figs, this really has endless sig figs, because when you count things, like me counting people, I don't count people as a half of a person, and I don't count pieces of French toast as a half of a French toast. It's a whole thing that I counted. So there's officially endless sig figs, but we're not going to worry about that right now. We're just talking about percent yield. So if I look at the back and do the same types of problems with a chemical reaction, first of all, I need to balance it. And by balancing it, I'm going to go, well, I need 2 oxygens here. That gives me 2 ZN, so I need a 2 here. That gives me 2 S's, so I need a 2 here. I'm going to do the same process I did with the French toast. And I have numbers written down here, so we don't have to worry about all the molar masses. I'll just give them to you in this case. So I have 2 amounts. I have amounts of each of the reactants. And the fun thing is we're going to figure out grams. So we get to go grams to grams. Yay. Now, if this was a standalone problem, the reason why I'm going to grams is because I see in number 2 here, I need mass of ZNO. If this number 1 was a standalone problem and the question was simply, what's my limiting reactant? You could just go 2 steps and solve for the moles of one of the products. It's fine. But since the next question is, what's the mass that's expected to be made, I'm just going to solve for that right away. And really, I could do grams of either product, as long as I'm consistent. But I'm going to use mass of ZNO, grams of ZNO here, because I know I need it in the next problem. So that's why I'm picking ZNO. Again, if it was a standalone problem, I could pick either product, as long as I'm consistent with both problems, and I'm comparing apples to apples, and not kiwi to tangerines. Now, this is grams, I forgot that. Now I just start plugging in my stoichiometry stuff. I need a mole here, ZNS, I'm going to have to cancel it with the mole of ZNS down here. I need a 1 mole up here of ZNO. I have to cancel that with moles of ZNO. I look at my balanced equation. This is a 2, this is a 2. I look at my periodic table, and this adds up to 97.48. I look at my periodic table, and this adds up to 81.41. It'll be the same here. I'm kind of rolling through this, knowing that we can add these numbers up, and I am giving you the process. Remember, anytime you have a mole ratio, those numbers are coming from the balanced equation. And anytime you have grams, that number comes from a periodic table. And it's always per 1 mole because it's a molar mass. If I put this in my calculator, I'm going to get 38.8 here, and I'll get 67.7 here. Which reactant, by looking at those two numbers, and I know that some of you are jotting things down yet, but as I look at those two numbers, which reactant is limiting me? If you're in third block right now, Matt Warzala, what's the answer? But since we're in second block while I'm recording this, Mitch, what's the answer? Yep, the top one is my limiting reactant because it gives me the least amount of product. So this is, right here, my limiting reactant. Right here. So the answer, and there's only one, the one answer is which one of the reactants limits me. The answer is the ZNS. This is one that limits me because it gives me the least amount of product. So the question is, what about number 2? What mass to be expected to be made? Jessica? Which mass of my ZNO should I expect to make? I'm going to look at either one of these two. Do you think it's 38.8 or 67.7? Yep, because? Yeah, it's limiting. Yep. Once I make 38.8 grams of ZNO, I'm out of ZNS. I can't make any more ZNO. It doesn't matter how much oxygen I have. Don't fall into the trap also of looking at my reactants and going, ooh, there's 46 grams there. There's 13 grams there. Well, there's a lot less oxygen. I'm going to have to run out of that first. Some people look at it and go, well, I don't even have to do it. There's a lot less of this reactant. It's for sure going to limit me. It depends on the mole ratios. It depends on the molar masses. And look at here, we can make almost, not quite twice as much, but a lot more ZNO with that oxygen. In reality, the ZNS is limiting us. So don't fall into that trap. It's a very, very scary trap. Now, if I'm doing percent yield, just like on the other side, I would take what is actually given, actually produced, 18.4 grams, divide it by what Jessica said is our theoretical, how much I should expect to be made. That is theoretical. Theoretical yield always comes from stoichiometry. If I'm asking you a percent yield problem, I have to give you the actual yield. Unless I'm having you do a lab and you math it yourself. But if I give you a percent yield problem, I have to give you that actual number there, like you see, the 18.4. When I do this math, I get 47.4%, which is not very good. Yesterday in your lab, most of you were between 95 and 100% yield. We have very good data. And yesterday also we had one reactant, so our limiting reactant has to be the one reactant. There's no choice. It only is a situation when you have more than 2 or more reactants. All right?